Okay. So today we are going to talk about jet bundles. So that's a way to think about derivatives for maps of manifolds. So, and that's what we're going to use to define the topology on the space of functions. So today we'll talk about jet bundles. Can you see well? Am I writing big enough?
I think it's okay.
Okay. So we can make the first definition. So let X and Y be manifolds and F and G be smooth functions. We say that F has order of contact K. F and G have the same derivatives up to K at a point P if when you look at all the partial derivatives, so if there is a chart, we have to look at a chart. If there exists a chart around P such that, well, sorry, my eraser is small. I think I'm going. Sorry. If first f of P is equal to G of P, equal to, let's say, Q, and there exists charts phi from U to Rn and C from V to Rm around P and Q respectively, such that all the derivatives, all the partial derivatives up to order K of F composed F composed with phi inverse composed with C at phi of X is equal to phi of P is equal to the partial derivatives of CG composed with phi inverse of phi of P for every alpha multi-index whose size is less than or equal to K. So I think everybody knows what a multi-index is. So by this, I just mean alpha is some alpha 1 up to alpha, and I should say also the jth component of this for all j from 1 to m. Okay, so if I take, alpha is a multi-index. That means that I'm choosing a partition of the number k. So I choose a sequence of numbers like that, and then the size of alpha is just the sum. And this notation, d alpha dx alpha, just means, well, d of this number, the partial derivative, dx 1 to the alpha 1, dxn to the alpha n. Okay, so this is a partial derivative of order given by this, say, j. Not j. Well, this size of alpha. Okay. So I think, I assume most of you have seen this notation before. If you haven't, this is what it is. So what does it mean for f and g to have the same order of contact k at p? That means that all the partial derivatives at p are the same. And they are taken to the same image. F and G are taken to the same image. Okay, so this is an equivalence relation at P is an equivalence relation. I mean, first of all, it's well defined. It doesn't depend on the chart. That's pretty easy to see because of the chain rule. And then you can check also that this is an equivalence relation. Okay. So now we can define the space of jets at P to be the set of points F, the set of smooth functions with this relation. Okay. So basically, this is called the kth germ of f, of a function like that. So you can actually write this as a disjoint union of jk of x, y, p, k, where you fix the image too. So k over y. Okay, so now this jk of xy, pk, is just the set of functions such that f of p equals to q, and then you mod out by this equivalence relation. Okay, and now you can kind of also take the union over all points p and define the total jet space. So the total jet space is just the disjoint union of the jet space, the jet space at P. Okay?
Can you say for what kind of problem that jet space is useful?
Well, that's what I'm going to do today and tomorrow. So you'll see it coming. But, you know, yeah, I mean, it'll be useful. I can say in a few words, but it'll be useful to define the topology on the space of functions. So let's look at some examples. I think that might help. So if X is a manifold, what is the one jet space of X R? Well, this is the set of functions which are smooth, and then modulo this case, this equivalence for 1. So the set of functions that are smooth, and then I just look at I take an equivalence relation when two functions have the same derivative. So actually, this at P for some P. So this is just the cotangent bundle of X times R. So why is that? Well, let's see what something here is. So what is a jet? So a jet is sort of the equivalence class of some function at a point P. Right? So this I can, map this to P, which is the point, and then I can look at the value of the function at P. So f here is a function from x to r. And then basically I can look at the derivative or the differential. So this guy here is the r coordinate. But if you look at the p and the dfp, this is exactly what you get to define what you have to define the cotangent bundle. Okay, so one way of thinking about the cotangent bundle is just to consider this the set of p's and derivatives of functions at p. Okay, so that's the one jet space. And similarly, if you look at the one jet space of Rx, this is just R times, well, if you look at that at 0, maybe that's a little easier to see. So this is, you look at curves, so from R to X, but you only look at them modulo equivalence relation at a point at 0. So this is the same as the tangent bundle at X. The tangent bundle to X. So, similarly, if you take the whole jet one bundle, that jet one space, you get R times dx. Is this clear, or would you like me to say more? Okay, so that's the one jet bundle. Let's talk about more, and let's get some more examples. Let's assume that we have two open submanifolds of Rn and Rm, and let's see what is the kth jet bundle of U and V. Okay. Well, I claim that there's a bijection between this and the product of U and V and some space of polynomials that I'm going to call. Well, let's simplify this first, and let's do R equals 1. Okay. So I claim that this is, there is a bijection with this. And what's A and K? A and K is just the set of polynomials in n variables, polynomials P, let me write it like this, P from Rn to R, such that you have 0 equals 0, so with constant term. What is this bijection? Well, given a function, given a jet, so this a jet is like a function and a point, basically. Then what I do is I look at the point is the first coordinate, the image of the point is the second coordinate, and then I look at the Taylor polynomial of f at the point P. Of order, this is the Taylor polynomial of order k minus f of p. Okay, so I don't look at the part. So if you, I think you all remember it, but let me just state what it is. So what's the Taylor polynomial? So this is f of p plus f prime of p times x plus f double prime of p over 2 times x squared. No, sorry. It's in higher dimensions. I should write it like this. So it's the derivative of f p applied to x minus p. Okay. And then I have sort of the second derivative applied to x minus p, and I'm going to write it like this, tensor power 2, so at the point p. Okay, so this is just the derivative of the derivative, and then so on, and then you have the kth derivative of f at p, x minus p to the kth power like this. And I forgot to divide by factorials. Okay? So, I mean, it's if you want, it's an exercise to see that this map is well defined and it's actually a bijection. So to see that it's a bijection, all you have to see is that given any polynomial, you can find a function at the such that the Taylor polynomial at that point P is that function. Sorry, it's such that the Taylor polynomial of that function at the point P is that chosen polynomial.
Professor,
Oi.
o AK, então, era para ter alguma coisa de K ali, era para ser
De
polinômio de ordem
grau,
K.
yeah, sorry, of degree less than or equal to K. Okay, so in other words, if you're trying to look at functions up to all the derivatives up to order K being the same at a point, then you just need to look at the point, the image of the point, and the derivatives in some way. So one of the, I guess the most canonical way to think of derivatives coupled together is to think of the Taylor polynomial. Okay? All right, so now, so I think that's the last example. And maybe it's not so hard to imagine that we can use this bijection here later to get charts on the jet space. But before that, let me just define a couple of maps. So if I have a jet, I know that this jet is over some point. So if I have sigma, a jet, I know that sigma belongs to jk of x, y, p. So it's a jet over some point. And I call p alpha of sigma. So it's the source of sigma. And then I also have a target. Sigma actually belongs to jk of pq. So we can split that into q's. And q is going to be the image, basically. So if you have a jet, the first information that you know is that it is based at a point on x, and it maps this point to some point on y. Okay, so a jet, again, is it's basically a germ of a function. Okay, so the first information is the point where you are, and then the image of this function. And then, unfortunately, the derivative, it's a bit more complicated to say what the derivatives are. Well, the first derivative is a map from tx to ty, but then the other derivatives are harder to explain, or are harder to really write down. So, yeah, so that's why we need this language of jets. Okay? So the point is, I mean, the definition of a jet is relatively simple, but what is good about them is what they, what you can say with the language of jets, basically. It simplifies a lot of the language. Okay. Yeah, so now we can define the push forward and the pullback of maps. So if phi is a map from y to z, which is smooth, then we can define a push forward on jets, which takes a jet from x to y to a jet from x to z. And what does it do? Well, if you have a function at a point, if you have the jet of a function at some point p, what this does is it takes f, you compose f with phi. And this is still going to be a jet at point p, but now it has values in z. Okay? You have to show this is well defined. So, basically you have to show that if f, so we need to show, maybe I should say this is an exercise. I mean, it's an exercise using the chain rule. So it's not very hard, but I guess you need to see that it's a necessary thing to do. So if F has order of contact K with G at a point P, so if they represent the same germ, then when you compose it with phi, then that's also G. Then they still have the same order of contact. So this is just the chain rule. Okay, so you can do this. And similarly, you can do a map. If you have a map on for the first entry here of jets, you can get a pullback. But it's still a little more subtle because you can't just do that for any smooth map. You need to have a diffeomorphism. You need this function to be invertible because of the following things. So, if you have a jet from X to Y, what you need to get a jet from Z to Y is, well, you have a function, you just compose this function with phi on the right. But now, if this jet was based at the point P, this will be based at the P. If P is not on the image, in particular, the thing is, if P is not in the image of phi, then there is no way to pull it back to a jet from Z to Y. That's why you need this condition of being a diffeomorphism. Okay, so it's a little bit harder to pull back jets than it is to push forward jets. And you should remember, from a class on manifolds, that something similar, there's a similar thing going on for differential forms and vector fields. So recall that it's easy to pull back differential forms but it's hard to push forward the vector fields. When I say that, I just mean the easy and the hard here. It just means that if you have any smooth function, you can pull back a differential form by it. But if you want to push forward a vector field, then you need to have a diffeomorphism. It's the same issue. Okay, any questions about this? Okay.
Up to this point, we're not giving the whole space JK any sort of structure, right?
Not yet. No.
It's just a set for now.
Yeah, so for now, it's just a set. That's all that said. But it'll be a smooth manifold. And these maps here are going to help us to define charts. Okay. So, yeah. I actually wanted to say one more thing before. I wanted to say that this bijection here is very canonical. So this is completely canonical. Given a function from Rn to R, we have this. Oh, yeah, I haven't said the case for m greater than 1. I'll get back to it later. Okay. And maybe I should say it's an exercise.
Professor, posso fazer uma pergunta?
Sim.
No exemplo que o professor deu, foi do jet indo de x para r, né? As funções indo de x para os reais. Tem alguma classificação de quando o conjunto dos jets vai dar um fibrato vetorial do produto das variedades?
Sim. Essa é uma ótima pergunta. A gente vai falar sobre isso daqui a pouco, mas eu posso falar a resposta rápida. Quando o contradomínio for Rn, aí você tem um fibrado vetorial.
Ah, legal. Obrigado.
Porque você pode somar funções, né?
Uhum.
Quando o contradomínio não for Rn, aí não tem uma forma natural de somar funções, de somar jatos.
Legal, obrigado.
De nada. But we're going to get to vector bundles and vector bundles in particular in this case. But for now, it's a set, and we need these technicalities here to define charts. So the exercise is that the pullback and the push forward are natural. So these operations, so the first exercise is show they're well defined. It's well defined, and of course you have to do the same thing here to prove this is well defined. But the exercise now is to show that these operations are natural. This means it means that if you take the composition of two, so phi composed with psi, and you look at the push forward, this is phi push forward composed with psi push forward. When you do the pullback, it's the same thing, but with the opposite order. Of course, if you have to assume that these two are diffeomorphisms. And finally, the push forward of the identity is the same as the pullback of the identity, which is just the identity map. Okay, so if you take the identity map from a manifold to itself, and then you push it forward or you pull it back, you still get the identity. Okay, so in particular, if phi is a diffeomorphism, then both phi star, both the pullback, the push forward, and the pullback are bijections. This just follows from these properties here. Okay, any questions about this? Okay, so now we can define charts. So consider now let sigma be a jet, and we're going to define a chart near sigma. And actually, this is going to define the topology too, because I define this jet space as being the disjoint union of spaces, but it's a disjoint union as a set. But it won't be the disjoint union with the topology of the disjoint union, obviously. So how do we define, the topology and the charts here? So, well, first we know that alpha has a source. Sorry, sigma has a source and a target. So it's based at some point P, and it has an image Q. Okay, this is well defined. So this is a point in X, and this is a point in Y. So now we choose charts. Phi, which is around P, so phi and psi, which goes from V to Rm. Around P and Q, respectively. Okay, and then the point is that now we have a map that goes like this. It goes from JK of UV to JK of phi of U, phi of V. So these are open sets in Rn, and Rn and Rn. And what's the map? Well, the map is simply you take some jet and you look at the pullback of phi inverse, and you look at the push forward. Sorry, this is psi. And you look at the push forward by psi. This is what the map is. Okay. I mean, it's very simple. You know, if you have the function, you just compose the function with phi inverse on one side and with c on the other side. And the point is that, you know, the naturality and the fact that these operations are well defined means that it is defined for jets. Okay, so you could, if you wanted, you could do it like explicitly. Just say, oh, take some function, and then you define this to be the jet of the function phi composed, c composed with f composed with phi inverse. Okay. But you know, you have to kind of always, when you talk about a jet, it's not the equivalence class of a function. It's the equivalence class of a function based at a point. So you have to choose the point when you choose the jet. And so this would be at the point phi of p. And so you could do that, this instead, go directly here. Okay, and because these maps, phi and c, are diffeomorphisms onto their images, then each of these two maps here, psi star and phi inverse star, are bijections. So that, in particular, tau of uv is a bijection. Okay, so we found the bijection from the set of jets of UV, which, sorry, I didn't actually say what this thing is, but I guess it's not hard to imagine. But this guy here is just, by definition, this set of jets such that alpha of sigma is in U and beta of sigma is in V. So the set of jets whose base is in U and whose target is in V. So a restriction. Okay, so what I'm saying is, you know, you can use these guys as a sorry, you have these charts here, and we have this bijection. So now you can use the topology on the space of jets here from Rn to Rm to define a topology on Jk of UV. And if you take U and V to be all, you know, you take all possible charts. So if you take, you know, an atlas, it doesn't even have to be maximal, but to just define the topology, you take an atlas of X and Y, then you have a topology. So yeah, and then we're almost there. You know, this is not just topology, but this guy here, it has the structure of a vector space. So Jk of, say, U tilde and V tilde has the structure of, sorry, it is an open set in some Rn. This is an open set in a Euclidean space. Okay, so this map TUV not only determines the topology, but it also determines a chart. Okay, so and sort of because it determines the topology, it's by definition a homeomorphism. Okay, and what kind of Euclidean space is this? So I didn't quite finish doing this before. I only did it in the case where the target is R1, m equals 1. But you know, what is it in general? So what is this guy in general? So there's a natural bijection. And you can basically just say equal because it's so natural. With U prime times V prime times, well, we have the space of n polynomials, but you have a polynomial function onto Rm now. So now you look at the Taylor polynomial for each variable. So a function from U to V from U prime to V prime, this is basically m functions from Rn to R. So you have this akn to the m. Okay, so this, yeah, I already said what it is. You can also, you know, write this guy, call this bk of nm, where bk, this is the set of polynomial functions from Rn to Rm of degree less than or equal to k, and then such that the constant term is 0. And the reason, one more time, I think you've probably noticed this, but it's because we're putting the 0th term of the Taylor polynomial separately, because it belongs to the target, it's very natural. And then the higher terms are more complicated. Sort of the first one, the first order, has to do with the derivative from one to the other. So this is like in the endomorphism, you can look at that like the endomorphism bundle from Tx to Ty. But then the higher derivatives are in harder and harder bundle maps. Which is why it's just better to talk about the jet space plainly. Okay. Any questions about this?
Vinícius, uma dúvida,
Oi.
uma
Que foi?
dúvida inocente, mas tipo
Sim.
assim, em vez de eu basear o jet, né, num ponto, eu poderia basear num aberto, sei lá, porque tipo, às vezes em variedades a gente fazendo, vamos dizer assim, nos pontos, né, mas sempre poderia fazer nos abertos, né? Aqui eu posso fazer isso também ou não?
Não faz sentido, na verdade, né? Porque você ter o mesmo germe é uma condição de um ponto, né? Uma condição para cada ponto. Quer dizer, faz sentido ou não faz, né? Faz sentido o que eu acabei de definir aqui, né? Que são os jatos em U. Isso aqui é uma restrição do conjunto de jatos. É a mesma coisa com o espaço tangente, né? O que seria o espaço tangente num aberto? Você pode pensar, bom, o espaço é a união dos espaços tangentes para cada ponto.
Certo, entendi.
Entendeu? Que a derivada é uma coisa que depende de um ponto, né?
Tá bom,
então,
obrigado.
Faz sentido? Beleza. Eu sei que I know that the definition of a jet and a jet bundle, it's a little bit hard to swallow, but it's really not very hard, but it's very abstract. If you can go through the abstraction, it's not very deep. And I can say it one more time, how do you get a jet? Well, you have to basically look at a function, a smooth function, and a point. But you look at that up to this equivalence class, which is that all the derivatives, or k, are the same. So this is called the kth germ of a function. Okay, so, well, actually, I should say that, because I think that's maybe a very important example or definition. So if you have a function, a smooth function, I'm just going to start calling it like this. So C infinity of xy is a set of smooth functions. Then we have a map, which is called the kth jet of f. And it's the following things. So it's basically the kth derivative of f. But in here, what you get is you get a map from J to the kth jet space. So this generalizes the idea of the differential. So this takes basically a point P and takes it to the kth jet of f at P. So this map generalizes the differential. So if you look at J1 of f, this, if you want, is basically the same as the map df. To be completely rigorous, there's also the value of the function is contained in the differential. So this at the point P is df of P, and then you have the value of the function. Okay. I hope this helps also understanding what the jet is. Yeah, go. Someone wanted to say something?
Eu queria fazer uma pergunta, professor.
Sim.
ali quando você definiu o JK de UV como sendo o target e o source em U e em V, você poderia pensar
Aham.
esse espaço também como sendo um próprio jato, né? Entre U e V. Você teria como fazer essa identificação? Porque você poderia pensar U e V como variedades também.
Sim, claro, claro. Exatamente a mesma coisa.
Mas aí você teria que fazer tipo, alguma extensão de variedade das funções usando tipo bump function, alguma coisa assim, para entender desse.
Eu acho que esse é o ponto, né? É que você é uma coisa completamente local, o jato. Então,
Tá.
você sempre consegue, né? E isso de repente é parte dessa abjeção daqui, de uma certa forma.
Tá.
Né? Que você escolhendo um ponto em U, um aberto, um ponto em V, no outro aberto, escolhendo um polinômio de Taylor, você sempre consegue achar uma função com esse polinômio de Taylor. Uma função definida no aberto que você quiser, né? Então você só precisa o primeiro passo é você mostrar que você pode fazer isso localmente. Você pode pegar o próprio polinômio de Taylor, né? Mais a função constante aqui desse ponto, né? E aí você tem que estender isso de uma forma que não vai mudar a derivada naquele ponto. Então você pode, por exemplo, multiplicar por uma bump function que é 1 na vizinhança daquele ponto e que é 0 meio que longe daquele ponto. E aí pronto.
Tá bom, tá bom. Obrigado.
De nada. Isso é para mostrar basicamente que essa aplicação daqui é sobrejetiva. Então, assim, para você ser bem correto, né? Isso aqui, na verdade, é um mapa e é uma abjeção, mas assim, a princípio é um mapa da forma que eu defini. Beleza? Foi o Luciano que falou?
Foi, isso.
Ah, tá. Valeu.
Uma outra dúvida, essa definição
Fala.
de jet também, ela não depende de se a variedade é conexa ou não, né?
Não,
Depende.
não.
Não depende, né? Uhum.
Não tem nada a ver.
Why this name, do you know? Why jets?
Why is it called a jet? I've never thought about that, but I don't know. I think the jet has something to do with, the tangent space and the cotangent space. Maybe it's because it has to do with like in one point you have a lot of information. So like all the derivatives at one point, that's kind of the information of the jet. So maybe that, I don't know, there's the imagery of, a jet of information from one point. I don't know.
Okay. Maybe it's because of the Taylor polynomial. They coincide until set points. So after that, So if you think about the jets of water, they starting kind of the same and change. So it's.
Oh yeah, like you're saying, they start
Yeah.
all similar and then at some point they go away. And yeah, it could be. That's
Not now about
interesting
that.
explanation. Yeah. Okay. All right. So,
Sorry.
No, fala.
Does it make sense to talk about these jet spaces when k is infinity? Is it interesting or something? The definition
Yes.
would be obvious, just all derivatives coinciding, but
Yeah, it is interesting. It's a very good question actually, because because we're really interested in talking about that same infinitive topology on the space of smooth functions, and we're going to use the kth jet space to talk about the kth topology, and you could go directly to the set of smooth jets. But I think the problem is that it's not a finite dimensional manifold, for example. Right? Because now the charts will be in the set of, are going to take values in the set of smooth, infinite polynomials. I mean, they're not polynomials anymore. They're series. And yeah, I mean, you could talk about, okay, first of all, are they formal series or are they convergent series? That's one thing you might have to ask. And I think what you want is just formal series. You just want all derivatives to be the same, but you're not requiring the function to be analytic from the beginning. But even still, this jet space, this infinite jet space, is an infinite dimensional manifold. So it, yeah.
Yeah, if we require the function to be analytic, we would have some sort of rigidity,
Yes.
right? We wouldn't be able to take two different functions in the same class.
Yeah, you'd have to look. Yeah, exactly. So it's so you probably don't want to require it to be analytic, but still it's more complicated because you see this jet. The nice thing is the skate, the jet space is a finite dimensional manifold. I haven't quite gotten there, but yeah. But let me just say one more thing related to your question, which is that if K is less than L, then you can think of the map that goes from JL to JK. That's just forgetting the derivatives from K to L. Okay. So this is kind of the forgetful map, if you want. I think someone's trying to come in. Okay. And, well, F. Well, let me just write it like this. So in some way, the space that you're suggesting, this infinite jet space, is what's called the inverse limit of JK of XY using these maps. This is an idea in set theory. Hold on, I think someone else is trying to enter. This is why I asked you to have the invitation. Okay. And as I said, you can talk about this. This appears in the literature, but it's a little more complicated, and I think I won't talk about it too much. Okay, so
Hello?
hi.
Hello, sir. Would you go back to the Taylor polynomial where you wrote that?
What the Taylor polynomial is?
Yes, so go back to the Taylor polynomial, please, one more time.
Here.
Yes, how are these higher dimensional dk defined?
How are these higher dimensional derivatives defined?
Yes, yes.
Well, you can define it like this. So recall, so if you have a function from Rn to Rm, you can define, you can say that it's differentiable. It's kth times differentiable at a point at P if there exist linear maps, but the linear maps are kind of complicated. So the first, so that you can write the function f of x as f of p plus, so I'm going to call this, well, dfp applied to x minus p. So dfp is easy. dfp is just a linear map from Rn to Rm. And then the second derivative, it's supposed to be the derivative of the map df. So the second derivative at p is a linear map from Rn to the set of linear maps from Rn to Rm.
Okay.
So you can finish this. Apply to x of x minus p. So when you apply this to x minus p, then you're going to get a linear map from Rn to Rm. So you apply it again to x minus p.
Okay.
And divide by 2. So you can do this, inductively. So sort of the kth derivative is at p is, the derivative of the map of the map dk minus 1 of f. So this is, if you want, the linearization of the map dk minus 1f, which goes from Rn, or from, it goes from the domain where the thing is defined, so Rn, to the set of linear functions, from Rn to the set of linear functions of Rn, etc., and then with Rm at the end. So you can think of this dkf at p as being some kind of multi-matrix. So this is like a n by n by n by n da 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 by n by m matrix. Okay, so that's why you can multiply this guy by x minus b sort of to the k, and the result is something. The result. Let me write it like this to the k, and the result is something in our m. Okay.
Okay.
Sorry, I wrote it in a sloppy way, but do you understand? Can you fill in the details?
Yes, I will fill in the details.
Okay, great. And this is the same, if you don't want to talk about these kinds of maps, you can everything partial derivatives, but it's just a huge mess to write it all up. But you can. So, well, what we're doing, we're talking about defining charts. So what we did is we showed that if I have if I'm looking at the jet space, the kth jet space from x to y. So what we said is that there is a bijection. There is a bijection from jk of uv. So if we have charts, then there's a bijection from jk of uv to jk of the image of u and the image of v. And this is an open set in a Euclidean space. By the way, what's the dimension of this Euclidean space? Can anyone tell me? Let me go back to see if that helps. So this guy, this guy here, the set of polynomial functions from Rn to Rm of degree less than or equal to k. This is this is an Euclidean space itself. And then U prime and V prime are open sets in Euclidean spaces. So the dimension is going to be n plus m plus the dimension of this guy. And what's this dimension? Is anybody good at combinatorics here?
M vezes K mais então.
M vezes K mais Não. Tem que ter n em algum lugar, né?
Espaço dos
Polinômios de n variáveis.
O espaço de polinômios homogêneos, alguma coisa com as formas simétricas, tem que ver a dimensão do espaço de forma simétrica.
Exatamente.
Somar tudo até a ordem K.
Uhum. Okay, it seems like maybe it's a little bit of a harder combinatoric exercise. It's not very hard, it's simple combinatorics. This is n plus m times, I think it's n plus k, here's n. I think that's what it is. Okay, because this guy, you can think of the sum here, these two guys as being the space of polynomials, of homogeneous polynomials of degree less than or equal to k. And that's the same as, sorry, you can think of this as polynomials of degree less than or equal to k of n variables. And that's the same as homogeneous polynomials of degree k. Is that? No, sorry, that's not true. Okay, my combinatorics, I don't know, let me not claim this. Let's do an exercise. Yeah, let me not get ahead of myself on combinatorics. And the exercise is compute this dimension. I mean, this is clearly m times the dimension of A and K. Okay, so you can do that. But in any case, this is a chart. This is easy to see. It's a Euclidean space. So we get these charts. Okay, so these bijections I was calling tau of UV. And now the point is, again, I'm going to leave another exercise. And you can see I'm leaving a lot of exercises for you. And maybe I'm not going to write problem sets. If you do all the exercises from the class, that's enough. Once in a while, I might do a problem set, but it seems like people are eager for exercises. So first, solve all the exercises from the class. And then we can talk about problem sets. So now, as usual, you would say, well, what if I choose a different bijection? What happens? So if you choose a different chart, phi tilde, that goes from U tilde to Rn, and psi tilde, that goes from V tilde to Rm, then we can write the inverse of this composed with this map. We can write these transition maps, UV, inverse, and of course restricted to where it makes sense. So restricted to the jet space, the intersection of U with U tilde, and psi of the intersection of V and V tilde, taking values into this jet space of phi tilde of U intersect U tilde, psi tilde of V intersect V tilde. Okay. So the exercise is to show that this map is smooth. Okay. And again, this is an exercise about understanding Taylor polynomials and applying the chain rule. Okay, so it's a little tricky, but it's not very hard. It's basically understanding this part here and then using the chain rule. So basically saying that if you take a function in some coordinate chart and you compose it with a different function in the front and in the back, then when you look at the derivative of that will be, this will be a differentiable map. That all the derivatives are the same and it's a differentiable map. Yeah, these two things have the same Taylor polynomials, basically. Anyway, so this is what the map is. And the point is that this gives, so JK of XY is a topological space, and it's not just a topological space, but it's a smooth manifold. Of dimension n plus m plus the dimension of okay. And here's a lemma whose proof, again, I'm going to leave as an exercise, which is that, well, the function alpha, the source function, the target function, and even the product of the two these are smooth submersions. Okay? So, well, let me say this is number one. So, the fact that they're surjective is pretty easy. And then they're submersions. Again, if you look in charts, it's really not very hard to see that. And maybe you see where we're trying to get, like this is starting to smell like a bundle. But as you see in a little bit, it's not a vector bundle. Okay, and the second comment is that if you have a smooth map from X to from Y to Z, then the push forward is smooth. So the push forward is a map between jet bundles, and this is smooth. And also if phi from Z to X is a diffeomorphism, then the pullback is a smooth map, but it's a bijection, and is also a diffeomorphism. Okay, and again, the proof is straightforward. Okay, so I don't want to spend a lot of time doing notation exercises that I think you would benefit more doing. Okay, so I set a lot of problems set. I set a lot of exercises, so I encourage you to do them all today. If you have time today, that would be great before we move on. Okay, someone's trying to come in. Okay. All right, so let me remark that we have these smooth submersions, but this guy, this jet space, is usually not a vector bundle. But if Y is equal to an Euclidean space, then this is a vector bundle. Over X. Right? Because if the target is a vector space, then you can sum functions. You can add functions, and that will induce an operation in for the jets. Okay, since you can define the pth jet to be just the sum. Sorry, you can define the other way around. So define the sum of two jets. To be the jet of the sum. Okay, and it's pretty easy to see. I mean, this doesn't depend on the choice. Okay. So now this is not a vector bundle, but it's another kind of bundle, and that's what I want to talk about now. Someone wanted to say something? I heard Mike.
I was going to ask what if it's a different kind of bundle.
Yes.
So,
Okay, so we're getting ahead. That's good. If I'm leading you to ask questions about what I'm about to answer. Okay, so this is called, what this is called a fiber bundle. So it's a more general thing than a vector bundle. So let me define that. So let E, B, and F be manifolds, and pi be a map from E to B, which is a surjective submersion. I guess maybe the fact that it's surjective, well, yeah, this might even be superfluous, as someone pointed out last time, but anyway. Then pi is called a fiber bundle with fiber F if for every B on the base there exists a neighborhood open B in U and homeomorphism from P inverse of U, it's homeomorphic to U times F, such that when you look at the diffeomorphism, the homeomorphism, sorry, I actually want to require it to diffeomorphism, because everything is smooth. This also holds in the category, in the topological category, but it's the C0 category, but I want to do it over C infinity, such that when you look at the following triangle, here you project over the first coordinate, if this triangle here commutes. This just means, if you take something here and you look at it U times F and you take the projection, that's the same as projecting it to U. This just means that, pi inverse of B is diffeomorphic to F. So this implies that the fiber over each point is diffeomorphic to F. So this is very similar to the definition of the vector bundle, except that you don't have the vector bundle the vector space structure on each fiber. So you can kind of draw the same picture, but sort of this. Let me see how. Oh, maybe the best picture is do something like this. So here's your base, and then here is the fiber bundle, and you project like this. And the point is that you can have sections of this. So a section of pi is a map S from B to E, such that pi composed with S is the identity in B. But the point is that if you don't have a vector, if each fiber is not a vector space anymore, it might be hard to find a section. There might not even be a section. So it's hard to see B embedded in E in general. You could find, an embedding of B in E, which is the image, which would be the image of a section, but maybe there isn't one. Okay, I can give you an example of a case where there isn't. Okay, so that's why you don't draw the B inside the bundle, because there is no zero section. There is no zero on this fiber, on these fibers. Okay, so this is what a fiber bundle is. So in other words, another way to say this is a trivial fiber bundle is just a map. It's just a product of a base and a fiber. And you can write it like this. The fiber always embeds. And a more general fiber bundle is a space that has a map, a surjective submersion to the base, and such that locally it's trivial. Locally, it's a trivial bundle. Okay, so this is what a fiber bundle is. So another way to say this is like basically you take a little neighborhood of B, you take the product of the fiber, and then you can do that for like a collection of open sets that cover B. And then the thing is how you glue these. So you glue these using some kind of homeomorphisms or diffeomorphisms of the product. And if you have the gluing information, then you can reconstruct the bundle. But that way with gluing informations is a little harder to explain. But it's actually the traditional way of talking about fiber bundles or even vector bundles. Okay? So a fiber bundle is just the same thing as a vector bundle, but you don't have the structure of a vector space on each fiber. Okay, any questions? So here, a simple example that satisfies what I said, where there are no sections, is, for example, if you look at, interesting, just one example, is if you look at the unit tangent bundle of S2. So this is the set of points. I mean, you can think of it as just being of S2 being embedded in R3 if you want. SXV. So this is a set of R3, S3 times R3. I mean, you can do this with abstract manifolds, but I guess might as well do it like this, such that V is tangent to S2. V is tangent to S2 at X, and the norm of V is equal to 1. Okay, so this is a unit tangent bundle. You can also, look at the abstract tangent bundle of S2, choose a Riemannian metric, and look at the vectors that have norm 1. Okay, that's the same thing. And the point is, so this is a fiber bundle over S2. And with fiber, can someone tell me what the fiber is?
S1?
S1, yeah. So for each tangent space is an R2, and if you look at what has norm 1 there, that gives you an S1, a circle. But the point is that you can't, this is different. It's not homeomorphic to S2 times S1. In particular, this bundle, this fiber bundle, does not admit a section. Okay, and this is because of the Harry-Ball theorem. This would contradict the Harry-Ball theorem. The Harry-Ball theorem says there is no non-zero vector field, non-vanishing vector field on S2. If you found a non-vanishing vector field, you could divide it by its norm at each point, and that will give you a unit vector field. Okay, so fiber bundles are, they're a generalization of vector bundles. They can be a little more complicated. I guess maybe we could talk quickly about the unit tangent bundle of S1. That's very simple. That's just S1 times S0. In this case, it is a product. But this is pretty easy because you just look at it, because the tangent bundle of S1 is trivial. Tangent bundle of S1 is just S1 times R. So when you look at the unit things, it's just S0. But I think what's even more interesting is the unit tangent bundle of S3. And this guy now, it's actually trivial. And this is because something that's very non-trivial, which is that the tangent bundle of S3 is a trivial bundle. So there is a bijection between this, a diffeomorphism between this and S3 times R3. Okay, so there is something. So when you look at the unit elements, you have a bijection to S3 times S2. Okay, this was just a little tangent about fiber bundles. But the point is that JK of XY now is a fiber bundle over X, over Y, and over X times Y. Okay, and of course the maps are exactly the, this is the source map, the target map, and the product of the two. Okay, so maybe this can be another exercise. And in fact, there's more. You can say that if K is less than or equal to 12, then JL of XY, the map from JL to JK is a fiber bundle. And then the second part of the exercise is, what is the fiber? Can someone say the answer to the second part? Describe the fiber. How do you know the fiber? So basically you take two L jets, you project them to K jets. So basically you forget all the derivatives from K, from K plus 1 to L. That's what this map is, some kind of forgetful map. And then the fiber is, if you look at a point like that, a K jet, what are all the L jets that are above it? So what freedom do you have what information gets lost when you project?
Polinômios de K até L.
Exatamente, polinômios onde os termos têm graus de K mais 1 até L. Exatamente. Isso é algum espaço fatorial. And here's a very interesting remark / exercise, is that when you look at this guy, over x times y, so J0, which is just x times y, this is the map alpha times beta, this is a fiber bundle whose fiber, with fiber, the fiber is just the BK of NM, so the set of polynomial maps from N to M of degree at most K, which are with no constants. So this is a vector space. So this is a fiber bundle whose fiber is a vector space. But it is not a vector bundle. And I think this is a very interesting exercise. It has to do with the fact that when you look at the transition functions, you don't get linear maps. You have these, you use the chain rule, which messes up the derivatives quite a lot, so you don't actually get, you don't get homomorphisms, linear maps between the fibers when you look at a transition function. So there is no canonical vector space structure on these fibers. Okay. What else did I want to say? Oh, the last thing I want to say today is that if you have a function, this gives rise to a section, so a smooth section. Of the bundle over X. So this is a map from X to JK of XY. Okay? All right, so I think this is all that I wanted to say about jet bundles. Next time we'll talk about the Whitney topology. So that's the topology on the set of smooth functions that's determined by jets, that's constructed from jets. But I think right now is a good point to stop.